Hello everyone. In this video, I'm going to walk you through how to answer questions in individual assignment. Six Sigma refers to philosophy and method that a company uses to eliminate the defects in their products and process. In this exercise, I will demonstrate how to calculate the defects per million opportunities. Statistical quality control covers the quantitative aspects of quality management. Statistical quality control (SQC) is a number of different techniques designed to evaluate quality in terms of conforming to meet specification set during product or service design. In this exercise, we will learn the use of capability index to measure how well a process satisfies design specification requirements. Managing quality performance using SQC technique usually involves periodic sampling of a process and analysis of this data using statistically derived performance criteria. So in this problem, a metal fabricator produces connecting rods with an outer diameter that has a 1 plus minus 0.02 inches specification range. A machine operator takes several sample measurements over time that has a standard deviation 0.007 inches. The sample mean outer diameter equals 1.004 inches. Based on this information, we can calculate the process capability. To solve this problem, we will first calculate the process capability using the capability index that's shown here. The capability index is used to measure how well a process performs in terms of design specifications. If the specification limit is larger than the 3 sigma allowed the process, then the mean of process can be allowed to drift before readjustment. The capability index CPK is calculated by dividing the ratio of the range of values allowed in the design specification by the range of the values produced during the process. In this question, the sample mean in this process is given as 1.004 inches. Since the design specifications on the product requires that the key dimension on it measures 1 plus minus 0.02 inches, the upper specification limit or USL equal 1 plus 0.02 is 1.02 inches. The lower specification limit or LSL equals 1 minus 0.02 is 0.98 inches. The standard deviation for the process is given as 0.007 inches. Substituting these values into these formulas, you can calculate the number of CPK. So first one is the difference between X double bar, the sample mean, and lower specification limit LSL divided by 3 sigma. The difference between sample mean and lower specification limit divided by 3 times sigma. And second component is the difference between upper specification limit USL and X double bar the sample mean divided by 3 sigma equal the difference between USL and sample mean X bar divided by 3 sigma. So it gives us the number 1.1429 and 0.7619. Since the process mean can shift either direction away from the mean, the direction of the shift and the distance from the design specification set the limit on the process capability. The direction of the shift is towards the smaller number. So we can use the mean function in Excel. In this case, capability index 0.762. If process capability index CPK is lower than 1, that means the process is incapable of meeting requirements. It will produce an acceptable defect. Based on this information, I will show you how to determine what percentage of items produced will be defective in this process. So we can calculate the actual probability of producing a defect using z-score normal standard distribution. To do this, we first need to calculate the z-score associated with the upper and lower specification limit. Z-score is the standard deviation either to the right or to the left of 0 in a probability distribution. Here is the z-score table. The z-score for the lower specification LSL is calculated by dividing the difference between lower specification limit and the process mean by the standard deviation. Assuming a normal distribution, the z-score of the LSL is equal to the difference of LSL and x bar divided by standard deviation, 0.007, which is negative 3.429. To get the probability associated with the z-value, we need to use the NORM as the IST function in Excel. We get the result of the probability for the LSL, which is 0.0003. Similarly, the z-score for the upper specification limit, USL, is calculated by dividing the difference between the upper specification limit and the process mean by the standard deviation. The z-score for the USL is the difference of USL, upper specification limit, and x bar divided by standard deviation, which is 2.286. So using the NORM as the IST function, we get the result of the probability for the USL, which is 0.98886. Z-score for the USL, 0.98886, is interpreted to mean that approximately 98.886% of the items produced will be below or within the upper specification limit. To determine the percentage of items produced expected to be outside the upper specification range, the z-score for the USL 0.98886 is subtracted from 1, which is 0.01114. Adding the two probability of defective parts together, we calculate a total probability of approximately 1.144%. Therefore, approximately 1.144% of the products made using a process mean of 1.004 will fall outside the design specification limits and be considered defective. 1.144% does not seem to be high defective rate, but it is critical in high-tech products like semiconductors. Let's move on to the next question. Statistical process control involves monitoring the quality of the process as it's operating. In this exercise, you will learn how to construct X-bar and R chart for a process. Here's the table for the 10 samples that were taken with the 4 items in each sample. So in this case, the sample size is given as 4 since it has 4 items, and the number of samples is 10 because each item has 10 samples. You are required to develop the both X-bar and R chart in order to identify whether this process is in control or not. Given this information, we will construct the 3 sigma limits for alpha and X-bar chart for 4 items. To construct the chart, first we need to calculate values for X double bar, R bar, A2, D3, and D4. X double bar, or the means of the samples, is equal to the average of each sample batch divided by the total number of samples. In X bar columns, we can calculate the average of each sample batch by taking the average of 4 items. Average of 4 items. So for sampling 1, X bar is the average of 4 items, which is 28.25. Next, you can drag it down to calculate the average of 4 items in each sample. And then to calculate the X double bar, we need to take the another average of all these averages. Average of all these averages. So X double bar is 30.36. Next, R bar is the average of the measurement differences, where R is the difference between the highest and the lowest measurement in each sampling order. To do that, we can use max and min function in Excel. For items and mean value in from item. The difference between highest and the lowest measurement in sampling 1 is 2.6. Next, you can drag it down to calculate the difference between highest and lowest measurement in each sampling. And then to calculate the R bar, we need to take the average of all measurement difference by using average function in Excel in R bar column. So average of all these difference. So alpha is 5.84 in this case. Next questions are to determine the upper control limit UCL and lower control limit LCL for X bar chart as well as the R chart. To do that, we need to use these formulas. First, to calculate the value of using these formulas, we need to refer to factor table exhibit A on the factor table sheet for getting the value of A2, D3, and D4. If you click the factor table sheet, you will notice that there are A2, D3, and D4 values based on the number of observations in subgroup N. This table has the information about factor numbers for determining 3 sigma limits for R bar and X bar chart. In this case, we have 4 observations in each sampling, so A2 factor for X bar chart is equal to 0.73, and lower control limit D3 factor for R chart is equal to 0, and upper control limit D4 factor for R chart is equal to 2.28 respectively. So A2 is from this table, D3 is from this table, and D4 also table. Next, we need to establish the control limits for X bar and R chart. Now, substituting the value in these formulas, the upper control limit UCL for X bar chart is calculated by adding the value of the average mean of the sample X double bar, which equal 30.36, and the product A2 0.73 and R bar 5.84, which is 34.62. Next, the lower control limit LCL for X bar is the difference of the same two values, or X double bar minus A2 times R bar 5.84 equal 26.1. Next, using the formula for the next question, the upper control limit UCL for the R chart equal D4 times R bar, which is 13.3. The lower control limit LCL for R bar is calculated by multiplying D3 and R bar. 0 times 5.84 equals 0. Now that we have all the required values, we can construct the X bar and R chart. So what are the conclusions of X bar and R control chart based on UCL and LCL you calculated? These diagrams represent the X bar and R chart for this problem. The upper and lower control limits for the two charts are depicted as red lines, and the dotted red line for each diagram shows the X double bar and R bar value, or the center line for each chart respectively, showing the average of these samples. We notice that all of the sample data points plotted on these two charts fall within the red lines UCL and LCL. Based on these observations, it is clear that the process for manufacturing these 4 items is in statistical control within 3 sigma confidence interval, despite there being some of the samples with the length below the center line, the average in the X bar chart. I hope you better understand quality control from this exercise. That's it.